Yeah, my name is Dušan Veličković. I'm a mass spectrometry imaging scientist here at EMSL. And today I want to talk about new in situ derivatization workflow that we actually developed for EMSL users. And I'm so sorry we didn't develop this before we analyzed Malak samples and also like Vimal stuff, because we could answer those questions, how, for example, pyruvic acids, where is ended and so on. But okay, we will do it for the next users or with Malak new proposal as well. So this workflow is designed actually to image carbonyls, but also phytohormones and other hard to detect metabolites by conventional mass spectrometry imaging in environmental samples. So interesting. Okay. So we heard a lot today about mass spectrometry imaging, about multi-mass spectrometry imaging. I also want to tell you that we will have a workshop that Kevin Zemaitis will lead, so you can hear even more about mass spectrometry imaging and future and where we see this can go and help in understanding environmental processes. Here I want to give you just fundamentals of mass spec imaging that you can understand and follow the story. Basically, it's spatial probing of sample surface chemistry by mass spectrometer. Idea is that by some specific probe, we go from position to position in the sample, acquire mass spectrum, and then that mass spectrum actually reflects molecular composition in that particular area of environmental sample, like, for example, in this case, root tip. So when entire imaging run is over, we ended up with those kind of ion images that represents actually relative abundance of that particular molecule over sample surface, like in this case, for example, adenine or hexose in the root tip. So the most common approach that we use here in EMSL, and we offer to EMSL users, but actually in general, most robust mass spectrometry imaging approach is multi-mass spectrometry imaging as probe. There we use UV laser to ablate and ionize molecule, and then those ions are analyzed and detected by mass spectrometer. So idea is that you need to have ions if you want to detect them by the mass spectrometer. However, many compounds are very hard to ionize. Some of them are also in very low abundance, like phytohormones, and then we fight with that sensitivity issues. Actually, also like some instruments, like for example, FTICRs has that limitation that cannot analyze very, very small molecules, like for example, pyruvic acid, and just because of the limit of detection, or yeah, just how instrument is built. And then it is reason why we decided in conversation with EMSL users and with what is important for the plant community and the environmental community, that we need somehow to bypass those challenges. So basically what we developed here at EMSL is on tissue chemical derivatization agent and the workflow that basically kind of you spray derivatization agent on top of your environmental sample, and that derivatization agent is covalently attached to molecules. In this case, this was designed to target mostly carbonyls, so aldehydes, ketones, carboxylic acids, and basically we put that tag there. We increase the mass of the molecule, so we kind of basically bypassing those challenges for really low molecular weight compounds analysis. But also what is important, as you can see, we introduce quaternary ammonium ion there, permanent charge into molecules, so we boost sensitivity of analytes, those that are low abundant, and also by having bromine in the molecule. You will see later on the 2 slides after this that we actually bring additional confidence in molecular annotation. Also, what is important in any imaging workflow is that we want to preserve original location of molecules, because this is what is actually really, really important here. And then also what this workflow enable to provide almost near single cellular spatial resolution by avoiding, we call it delocalization of molecules diffusing out of their original location, which is particularly difficult to achieve when you analyze metabolites. And then, of course, the great advantage of the workflow you will see later is that we were able to increase molecular coverage of analytes that we can detect. So this is just one figure that show how this workflow actually can help in expanding molecular coverage of analytes. Here you can see that usually with this workflow, depending on what sample we analyze, but in average around 300 to 400 molecular features we can annotate, and 100 of them are actually previously undetected by our conventional mass spectrometry imaging workflow. And this workflow, you can see actually that it's a little bit biased toward aliphatic carbonyls. So basically, we can analyze very efficient free fatty acid, so from short to long chain fatty acid components of TCA cycle, amino acids, and also phytohormones. So this is biased toward aliphatic carbonyls, but we can still really efficiently can ionize even aromatic carbonyls, like many of phytohormones are like that. And this is a step also very important, how we bring additional confidence in molecular annotation. I said at the beginning that this derivatization agent actually has bromine that is introduced into analyte, and bromine has two stable isotope, 79 and 81, that have relatively same abundance. So basically, that isotopic pattern is very easy recognizable, and our bioinformatic framework that is behind automatic annotation. So we use metaspace in this case very efficiently with low FDR. Can be confident that what we detect is actually particular compound. This is actually especially important for low abundant molecules, because all our annotation is based upon MS1 data, so based upon a fine isotopic pattern. And then in the low abundant molecules, like for example phytohormones are, you usually don't have like C13 isotope is often below limit of detection of instruments, so we don't have anything to compare with. And there we come to another important point, and it is that we don't only want to match theoretical, that is those blue traces, with experimental, those are red traces, like intensity of the peaks. We also want to match, and to if molecule is that for real, then also like spatial distribution of those isotopes should be same. So they should all colocalize together if you want to have confident annotation, like for example in this case. So all isotopes very almost perfectly colocalize one with each other. And now we come to application of this workflow. We originally designed this as part of S&T investments to work on the plant systems, like on plant tissues, like root, stems, and so on. We use the poplar root. We also use soybean root nodule as part of development. And then you can see that we actually can describe entire TCA cycle. We can also see distribution of many phytohormones in the poplar root, and some of important aliphatic and aromatic carbonyls in the soybean root nodule, most of them involved in biological nitrogen fixation. So this is also very important to highlight that with this workflow, we can have really cell-specific signatures. And this is, again, also part of Amir Kami CSPOR project, where we were investigating how drought actually influence poplar. And you see here, we, for example, imaged and find localization of MDA. This molecule is malonyl dialdehyde. This is very small molecular weight compound that we would not be able to visualize without putting that tag there. It is also a volatile compound. But in the essence, it's very important in the drought stress, because it's a product of lipid degradation by a reactive oxygen species. So it can be really used as a drought indicator. And here you can see that we located this molecule actually in the vascular part of poplar root. So this workflow was designed on plant organs. However, we actually optimized it, and this is also part of Kevin Zemaitis' work, of Jade as well. She provided us those rhizochips. So basically, it can work on several EMSL user samples that we accept from the EMSL users, that we work there to investigate that spatial organization of metabolites. This is like example of the rhizochip, or today we call them terraforms. So we're basically, before in our conventional workflows, we were able to maybe annotate like 40 molecules. Now we can detect like 10 times more. And you can see that they have really different spatial distribution. Some of them associate just with the root. Some of them are just beside the root, like root exudate. Some are just come from exactly the root. Some of them, like glycolate, their upper have like really some hot spots that are away from the root. So maybe have information about some microbial activity that is going on. So really also different type of molecules, from amino acids, derivatides, decarboxylic acids. Really a lot of different type of molecules we can visualize there, and different distributions. Some of them are also between the pores, because this is synthetic soil habitats, and you will also be able to learn more about that on the workshops on Thursday. And then also very interesting is that another type of sample that we often receive from the EMSL users are microbial interactions, so microbes that are grown on the agar, and users often interested in how those microbial exchange occurs. So we adapted this workflow to be adaptable and applicable to those type of samples. And here you can see this is in collaboration with Arunima, that we investigated interaction between Bacillus subtilus and Fusarium that are growing on the solid agar plates. And what I want to highlight here is that before was very big challenge to analyze acidic compounds directly from the agar. So because those acidic compounds are usually like negatively charged, actually we need to transfer them into negative ions in the using negative ionization mode, but that was not compatible with the agar chemistry, and due to the negative charge as well of the agar. So it is reason how by using this workflow we bypassed this challenge by converting all those negative core acid compounds, converting them into positive charge. Remember that this derivatization agent has that permanent nitrogen there, and then we can actually analyze again more than 400 molecules. We can visualize here. All of them have like, or those are some highlights of some different spatial pattern that we observe. Some are more present in the interaction zone between Fusarium and the bacteria. Some are more present in isolation culture. Some have a really specific location in the interaction area, and so on. Just to highlight that this is also one of samples that this workflow can be applied. And if you want to draw really true biological conclusions, and you need to fight with problem in mass spectrometry imaging, especially in the MALDI, where we use only MS1 for molecular notation, and then there are many molecules. We call them mass isomers. They have exact same mass, actually exact same molecular format, just those atoms are differently organized, and those molecules can have different biological role. And then we need to be really cautious how we annotate those molecules. You will see that usually we say like this is hexose. We cannot say it is glucose, fructose, or something like that. So we really need to be careful how we annotate those molecules. But in terms of differentiation between some of the isomers, this workflow can be really efficient, especially in differentiation between aldehydes and ketones versus carboxylic acids of the same mass. You can see that if we want to derivatize carboxylic acids, we need to add activator EDC. Without it, carboxylic acid would not be derivatized. So in that sense, we were able, for example, to really ascribe this molecule as a for example, in this case, butanoate and acetoin. They are both microbial fermentation products. However, one, you can see butanoate is completely carboxylic acid, acetoin is ketone, and then we can, by using this workflow, actually differentiate between those two compounds. Similar case is with malat, that is again completely carboxylic acid, decarboxylic acid, and dehydrothreonate is oxo acid. It has that keto group. So basically, this is just kind of summary or conclusion of this talk, that basically EMSL users using this workflow can actually now resolve roughly 300 to 400 molecular features in their sample. 100 of them are completely new that we were not able to provide them before. And also, we are now more confident in molecular notation of those compounds. This is very efficient if system that you investigate involve the carbonyls, and that is, I mean, carbonyls are involved all from the molecular signaling, membrane fluidicity, some are toxins as well. So there are really a lot of applications where this workflow can really shine. And of course, this is again applicable to different type of samples, root cross sections, stems, leaves, but also like our microfluidic devices and microbes that work on agar. With that, I would like to thank you, and yeah, I'm open for questions.
Great talk, Dušan. I think we have time for 1 to 2 questions. Coming back in with the microphones, but I'll bring this to you for the moment.
Thank you very much for your insight. I was wondering if this technique can also ionize metal-based organic compounds, whether it's easier than just organic-based compounds. And second question is whether mineral-organic interfaces can be visualized and characterized too.
I think that you will hear better that with on the SIMS talk that we will have like later this week for the elemental analysis. But here, like we can analyze organometals, for example, heme as like one of the compounds. We were like I would say very easily we can detect them, for example, in soybean root nodules. So yes, it can be used for tracking siderophores or those kind of compounds very efficiently. So we already demonstrated, for example, heme B in the soybean root nodule, how it's asymmetrically distributed there.
They're like internal compounds, but how about the external soil, like water leachate, water-based organic mineral?
So I think that we also like investigate. We cannot. I mean, you know, where is here what problem is that you need to put. I mean, this particular technique, all ions will be. So let me start from actually original MALDI workflow, right? So it depends like what. It's hard because like to ionize molecules, you need to add either like some alkaline ion to be like to convert it in the ion, right? So usually like what we see like when we analyze, let's say some compounds, they are already in the like potassium or sodium or sodium form, right? So that is like inherent to the MALDI process, right? But in your case, I think that I know that with Arunim, I don't know if she's here, like we investigated some of the organic acids and how they actually, yeah, kind of complex with the metals there, but we don't see them as such, right? Because this is all those ions will also like associate from this. So this is not great application for the work that you were just asked. So
thank you so much.
Welcome.
Awesome. I think we have one more quick question over there.
Hey, Dušan, very nice talk. I was wondering, do you think this is compatible with like flux analysis? Like when you add like another isotope on top and then also the timing of the derivatization is gonna quick enough to allow that?
Yes. So I mean, entire our so for example, like what this workflow, I'm not particular this workflow, but in general, like our FTICR, and Kevin can talk about that on his workshop. We kind of struggle to trace like for example, experiment that Malak we're doing like with C13 enrichment. It is very hard due to the FTICR to really know if we have enrichment or not. So in that sense, this is like FTICRs are not great instruments for that. But yeah, we can definitely add not only like bromine, I mean bromine facilitated molecular notation just because of those isotopic patterns. So we can basically introduce any other halogenic compounds that have like those stable isotopes that are very easy to spot here, right? So yes, I mean that's very feasible to do.